Hello.
Apologize for this was standard material, so I hope that you will follow from other talks. Okay, so this is the probability of x0 given xt. Uh, so this is a posterior probability, which is a quite difficult object to compute. Right? But then what you're doing is that you're averaging this vector here under the posterior. And this is a very interpretable vector because essentially it's the pointing direction, is the pointing direction to x0 if x0 was the only data point. So if you have only one possible data point, this is just minus the noise, which is obvious, right? If you have a single data point, you can, and you are in a noisy state xt, you can just subtract. The data point is fixed, so you know what it is, you can subtract it, and it will just give you minus the noise, and this minus the noise will point you towards the perfect denoising direction. And in that case, if there is a single data point, you can denoise in one step, okay? What you get that the vector field averages over all these pointing vectors corresponding to the noise from each individual data point under the posterior distribution. Okay? So it's if you have multiple data points around you and they're pointing like in different directions, the resulting score will be an average between the two. Okay? You see? So if you are in this noisy state here and you're asking where it comes from, the score will point like this.
So in practice, every x0 corresponds to something from your training data.
Either the training or generally from the distribution. So if your model is generalizing, then they are not just the training data, but they're also points out of the distribution itself. If the model is fully memorizing, then those are only from your training data. Okay, so we will go back. So again, for a single data point, you see that you have a single noise factor, right? And you can easily compute what the score is, given the fact that essentially you have a data set of single data points. And the last thing is you can also see this as a one sample estimator. So if you have the score, you can take a one sample estimator of the score that comes from this formula. Now, how do we learn the score? Well, the nice thing is that we have a one sample estimator. So if we have an unbiased, and this is an unbiased estimator, right? If you have this, it's an expectation, you take one sample from the expectation, you will get an unbiased estimator. So it's very easy, if this is a noisy image, this is a noisy image, noiseless image, to construct an unbiased estimator of the score function. Unfortunately, we cannot use this estimator during inference. Why? So during actual denoising, we cannot easily use this estimator. You know why?
Don't know where you want to go.
You don't know where you want to go. So this is an estimator of the score somewhere, but not necessarily of the score where you are, because you will need to be extremely lucky. So the way you do this is you sample the image first and then the noise. And that's not going to land exactly where you are, right? So it would be, yes, it is a one sample estimator, but you can only use it in reverse. The nice thing is that training is effectively done in reverse, right? For training, I don't care about training the score at a given fixed point. I just care about training the score everywhere. Or what I can do is that essentially if I have a one sample estimator, I can have a loss to try to predict this one sample estimator. And if I use a squared loss, you can easily prove this kind of standard result, like Euclidean diffusion theory, that the optimum of this loss is the actual score, okay? Because the optimum of square loss is the expected value of the estimate, okay? This is quite a standard result. So the square loss in diffusion, it's actually mathematically principled. It's not just a choice that we make, it's actually a mathematically principled choice. And it is due to the fact that our target is the expected value of the estimator inside the loss. Okay? So the loss, this object will be optimized. If you have a perfect network, so a network that has so many parameters and you train enough, it will converge to the correct score function.
Why are there two twos on the right? The upper and
Oh, the L2 norm.
Okay.
It's just the L2 norm square.
Yeah.
So we move to the kind of things that I've been doing. So it turned out that this generative diffusion model have a very interesting dynamics during generation. So for a lot of this talk, I will talk about you take a trained diffusion model and you And from the trained diffusion model, you see what's happened during generation. And it turned out that there is a very kind of rich dynamics that happens when you actually sample from these diffusion models. And it shows up even in very simple cases. So what we did, like in 2023 for this work, is to analyze kind of how the diffusion model takes decision in the sense of deciding what to generate when we initialize the trajectory. And we use this concept from physics that is called spontaneous symmetry breaking. And the idea in physics, the idea is that often you have like an underlying symmetry. Like for example, like from statistical physics, you have that if you have a spherical magnet, in general, the spherical magnet is a rotationally invariant object. So its description will not change if I rotate it, okay? Because the shape is spherical and we assume that the structure is small enough that does not induce anisotropism. So that's the history in statistical physics. The equation describing a spherical magnets are rotational invariant. But you know that if something becomes ferromagnetic, then it will generate its own magnetic field, right? A magnet generates a magnetic field, but the magnetic field points somewhere, okay? And since the magnetic field points somewhere, it breaks breaks the rotational invariance. Now, if I rotate it, things change and dragging the magnetic field around, okay? So how is it possible that laws of physics that are invariant under a symmetry can break that symmetry? You see, because it feels that there is not the law does not have information. The law of physics does not tell you where the vector is going to point. So that's extra information that is not in the laws of physics. You know, what it happens that in a real magnet, essentially a magnet when it is in very high temperature does not generate its own magnetic field. Okay, because the atoms inside are just moving too fast. As you decrease the temperature, you will see that there will be a phase transition that is called the symmetry breaking phase transition, in which the atoms will want to start to align. And at that point, at the critical point of the phase transition, so essentially, if you get a potential function like this, imagine the microstate of the magnet. At high temperature, the potential function will look like this. Do you know, like from physics, what is a potential function? So essentially, a system wants to go to the state of minimal energy, usually a statistical system. Therefore, if the atomic system starts to getting excited, usually it will relaxate back to the point of equilibrium. Okay? So it means that microscopic fluctuation do not change the thermodynamic equilibrium because they are pushed back to the minimum of the energy by the system. At the criticality, you have that the barrier that is stopping the noise, it actually vanishes. Okay? So the point of criticality is defined as the time where the quadratic potential around the optimum disappears. If the quadratic potential disappears, like let's do again the example of the magnet, you will have that small microscopic fluctuation now can be amplified to macroscopic ranges. Okay, because there is nothing blocking there. Before, there was impulses of the noise, the random noise, but they were blocked. And now they can cascade. And what's happened right afterwards is that the potential will split in a series of equivalent minima. And the thing that is important to remember is that the shape of the potential throughout this transition is still symmetric. You see, in this case, it's like an Ising model. So it's a +1 to -1 symmetry. Okay. But you see, the shape of the potential throughout seems symmetric because the laws of physics, and in this case, the laws of the generation, are regulated by a symmetric function. Okay. But the individual particle will need to make a decision. And before this time, the noise is suppressed. You see? Because the potential is a single minimum. So if the noise tries to go in one direction, it's going to be pushed back. At some point, the barrier of potential will disappear and the noise is not going to be pushed back. So the noise can actually propagate. After, the neutral stability becomes instability. And therefore, the action of the noise is going to be amplified by the instability, and the system will roll towards one of the new minima. And once the system gets into one of these two, in this simple case, two new minima, the system gets trapped again. So it gets again in a trap, but this trap breaks the symmetry. So from the point of view of an individual particle, now it's either left or right, and it cannot realistically mix anymore. Okay. Um, this is essentially what's happened like in statistical system, like when they have a symmetry breaking, and this is also what's happened during the dynamic of a diffusion process. Essentially, you have this stochastic process for a while, the noise essentially does nothing. At some point, the potential kind of flattens, and now the noise is able to spread, and the noise here will have an overwhelming impact on the final generation. You see? So if you think about diffusion initially, maybe you can think that the noise is important throughout. Actually, mostly the system decides around here, and here, as you see, nothing happened, right? Essentially, all perturbation are, you see here, the trajectories are fully separated. So all perturbation are reversed. And here, the trajectories are fully mixed. So again, perturbation are reverted as well. So the only separating factor come around here. So what we here is that, so this is a very simple example with two delta function, which the symmetry is just the fact that the two delta function have equal probability mass. Here we actually do that with train models. So for two arbitrary images, and then we compute their potential just by integrating along the surface of the train network. And you see that you will see a similar phenomenon. Of course, in this case, the symmetry will not be an exact symmetry, right? Because two given images will not end up having the very same probability, but you will see the same splitting phenomenon.
Do you see a critical point where you sort of see transitions between phases?
Yeah, it's you will be able to
there. And then you can see the system oscillate for a while.
So you can do kind of U-turn experiment. So if you start in one point, you can add some noise and then go back.
Right. Yeah.
And that allows you to find that there will be quite sharp places in which a lot of features are set. So you will have that some feature will really be set around some specific points. Okay, so I don't know if you guys are familiar with statistical physics, but it is quite interesting. How many of you are familiar with statistical physics? Okay, actually. So it is interesting that if you try to characterize mathematically this point when the potential vanishes and the structure of the fixed point, so the fixed point equation of the score, you will get into an exact Curie-Weiss model. Okay? So the diffusion process is an out of equilibrium process. If you actually try to study the fixed point dynamics and the shape of the potential, you get exactly into Curie-Weiss theory. And it's not an analogy, that's exactly the same formula. So you get into exactly the same theory. Okay. So it's an interpretation, right? Because in this case, we are studying an out of equilibrium process. So the Curie-Weiss theory describes not the dynamic of the system, it describes the structure of the fixed points. Okay?
Yeah, I also have questions.
Yeah.
Curie-Weiss model is derived for on-to-on or fully connected network, no? But this is like multi-layer and crazy architecture. How can it?
So this specific formula comes from the exact score. So I'm assuming that I take the exact score function. If you have two delta points, okay? So if you have two delta points, you don't need a network. You can just compute the exact score function.
Okay.
Okay? And then you can show that the fixed point structure of the exact score, which is the optimum, right? Even if you use a complex model, you will learn the exact score at the end. So the exact score embeds in its fixed point structure for Curie-Weiss theory.
And even in the general dynamical system for neural network, the Curie-Weiss solution only appear as when you are close to Gaussianity, no? Because if you have a rate model, so like x dot b minus I can then some integration function, then you have the Curie-Weiss model as a solution of the dynamic, but that solution you also work under the assumption that the network have some given architecture, no?
In this case, it's a property of the optimum. So regardless to what the architecture is, if it converges to the optimum, it will inherit the Curie-Weiss structure. You know? So this theory applies to all networks. A network will fail to learn the optimum. But in this simple case, you can, if the network is large enough, you will actually learn it very reliably. You know? So a lot of theory can be done essentially just by looking at the distribution of the data without looking at the network at all. And after we will discuss a bit what's happened when you put the network in the mix, but you can just do a lot of stuff just by studying what the exact score is under some data distribution. And often you will see that the network for decently large fraction of noise levels will inherit the same structure of the exact score because it's a structure of the solution of the solution of. Okay, so you see that the fixed point is regulated by the intersection of like hyperbolic tangent and straight line, essentially, like in Kurivaisa, actually is an exact Kurivaisa theory. Again, you need to be careful with the statistical phasing interpretation, right? Because this is a finite system, it's one dimensional. In this case, there are two deltas, right? But you see, a Kurivaisa model, in some sense, is a model of an infinite system, an infinite fully connected system, right? So that's a bit of the kind of mysterious fact that if you have a dynamical system, the bifurcation structure of the dynamical system can become formally equivalent to actual phase transition in equilibrium system, or in infinite equilibrium system. Okay, this is a big source of confusion. Okay, so if you want, call that a bifurcation. It remains the fact that this bifurcation is formally identical to an equilibrium phase transition. But the correspondence have a bit of a different interpretation. So what does it mean? Like, what you have divergences, right? You can see in the fixed point structure that the system has the same kind. It's Kurivaisa, so it has the same divergences. So what does it mean for what is the divergence showing up in diffusion? Well, an obvious one, for example, is that if you tilt the probabilities, so if you add the limit of field and you tilt the probability between the +1 and -1, it will create a jump. So what will happen is that the path of fixed point becomes discontinuous. Okay, so in terms of equilibrium physics, it will tell you that a second order transition becomes a first order transition. And the divergence of the critical exponent, so the divergence of the statistics tell you that there is this, any small fluctuation will give you a finite jump. So that's the infinity. Okay. So you can observe this kind of call them bifurcation, phase transition, what you want to call them, but you can observe quite reliably in a train diffusion model. Now, it used to be easier a few years ago because it's a bit of a sign that the model is not really well optimized. But essentially, this is a DDPM model, like a paper like for 2022 model, right? But so what you see is that you can essentially initialize for most datasets, you can initialize the model quite later on. So these are essentially, this is the initialization time. The initial DPM goes from 1000, it has 1000 time point. And this is FID. So FID is a measure of image quality. Okay. And they could show that for this DPM model, you could initialize them very later on without essentially affecting FID. And all of a sudden, then FID starts spiking up. Okay. And this comes from that essentially for half of this denoising trajectory, the model was just oscillating around this fixed point. So it was not doing anything at all. So you were using a very expensive neural network just to kind of oscillate around the fixed point. And at some point, the fixed point destabilizes. And then you see that they get a very big spike in FID. So the image quality becomes quite reduced.
So ideally, you would just have like a constant slope, I guess.
Yes, you can. I mean, we try to formalize this information theory now, so I guess you will find that interesting because that's this is FID, right? So it's not a quantity that is super meaningful theoretically. So what I would say that ideally you will have a constant slope in entropy production, or a constant level of entropy production. That would mean it's not exactly like that, but that's my intuition. So a nice kind of application and kind of intuition that I want to give you is that in generative diffusion, different decisions are taken at different times, okay? And my standard analogy is that imagine that you're driving in a highway, okay? In the highway, there are some fixed exits, you know? Maybe you need to go east, but you're just not allowed to just drive east just because you need to go east. There will be a specific time in which there's an exit. And either you take the exit or you miss it. And if you miss it, you're going to go several kilometers straight, you know? So imagine that you're generating like humans, right? And humans can get in different varieties, right? Like races, as Americans would say. And well, usually data sets have some sort of imbalance. So usually the way you interpret is that like if you take like a Western data set, like for example, 70% of people will be white, right? So it means that there is a big white straight that gets most of the probability, and then there are some exits, you know? This means that in diffusion, often you don't want to use 1000 function evaluations, okay? Because that's very expensive. Each function evaluation uses the whole number. So in diffusion, often you want to reduce the number of function evaluations to something like 10, 5, okay? And now imagine this is kind of equivalent that if as a driver, you kind of get distracted more time, okay? In the sense that you're not really updating your So imagine that you have these exits, and now if you have few function evaluation, you're probably going to mix an exit. If you miss an exit, eventually you are defaulted in the main class. So what's happened is that this is like the ethnic diversity, and if you use less function evaluation, it will shrink. So it will actually enhance the bias. And I feel this was just a bit of a discussion in the past, right? Can machines be racist? Obviously, machines are not racist, but it is true that models that are badly calibrated can enhance existing biases because they just will. So it's not that they just reflect the bias, but they can actually make it more severe than what is intended. So the nice thing about what we did here is that if we do this late initialization, so we initialize the point right before the symmetry breaking, then essentially with the same number of function evaluation, you can restore the full diversity because you're essentially initializing right before the decision point. Yeah.
So with function evaluation, you mean the number of
time
noise levels at which you calculate gradients?
Exactly.
Good.
Exactly. So you need every time you want to calculate a gradient, you need to pass things through the neural network.
Sure.
Okay. All right. Okay, so one thing that I've been doing in the past couple of years is to connect this concept of spontaneous symmetry breaking with some concept from information theory. What's the reason is that symmetry breaking is a property of the potential energy at the point of instability, at the fixed points. And these objects are very difficult to study in neural network, okay? Because essentially what we study is the stability of the dynamics around the equilibrium point. Unfortunately, in high dimension for a diffusion system, the equilibrium point is never visited by the samples, okay? Because in general, the system is noisy, so the system will never sit exactly at equilibrium. And the higher the dimension, the more is unlikely for the system to sit exactly at equilibrium, okay? But the way we study symmetry breaking, that we study the onset of instability at the point with zero noise, at the point of equilibrium, okay? And the problem is that the network is not trained there. So if you actually try to study that point, you will see that it will not give you any is not trained in that thing, so it will not give you any information. Okay, so we can only study really the network in what can call the entropic shell. Okay, so it's a shell of particles that live around the equilibrium point that will incorporate the fact that there are fluctuations around the equilibrium. Okay. So the next thing is that if you look at information theoretic quantities, and the quantity that I really prefer to study is this, what they call the generative conditional entropy. And the generative conditional entropy is the entropy of x0, so the starting point, given xt. Okay. So given your current noisy state is essentially looking how much uncertainty there is about x0. And this up to an additive constant essentially is kind of the mutual information between x0 and x0. And what you can study is the derivative, is the temporal derivative of this conditional generative entropy, because the temporal derivative tells you what essentially how much things are happening at a given time. Okay. And effectively give you an importance of the time point. Because if the conditional entropy is very high at a given time, if the conditional entropy rate is very high at a given time, it means that you are losing a lot of information during the forward process at a specific time, which is also means that you are inserting a lot of information in the process at that time. So from the point of view of the forward process you're losing, from the point of view of generation, you're actually transmitting information. You know? So in some sense, this conditional entropy rate give you a measure of generative bandwidth. If you imagine the system to gradually transmit bits to its so imagine the diffusion system to be gradually transmitting to its final generation. Okay, so the receiver is the final generation, and you're gradually transmitting. The rate of transmission depends on this conditional entropy rate, and the conditional entropy rate has a quite beautiful closed form solution. Okay, so the conditional entropy rate, so these are so-called IMMC formulas, can be expressed in quite a beautiful way, and is related again to the Jacobian of the score function, to the trace of the Jacobian of the score function. And then you're going for me because that's the same things we were actually studying before, right? Before we are studying the eigenvalues of the score function around the point of equilibrium, while the conditional entropy rate is a function of the Jacobian of the of the trace of the Jacobian, but not in the point of equilibrium, because this is average over the actual position xt. So now you're looking at the Jacobian in the entropic shell. Okay, so that is a quite of dual quantities. One looks at instability at the equilibrium point. The other looks at stability and instability in the entropic shell itself. And the nice thing is that this object is very easy to estimate on real level. Okay, why? Because the model is trained on the entropic shell. Okay, so in that shell, actually, the model is well trained, and we can easily probe the Jacobian and its trace and eigenvalues. And so, again, this is quite an intuitive quantity that can be expressed in many ways. Like from the point of view of the dynamical system, it's nice to express them in terms of eigenvalues because they tell you a lot about stability and instability. So effectively, so if you just plot, the eigenvalues essentially will tell you they are second derivatives of log p, right? Because this is the Jacobi matrix of the score, which is the first derivative. So the second derivative of log p tell you if a point is currently stable or unstable. Okay, and the entropy come when we take these eigenvalues in expectation. And you will see that spikes in conditional entropy come from points where these eigenvalues are negative. Okay, negative because we're going in opposite time. So in opposite time, negative means unstable. Unstable and positive means stable. Okay, it's a bit of source of confusion. So if you go in this direction, for this direction of time, you will see that you will get negative eigenvalues here, and these negative eigenvalues essentially cause a spike in entropy production. So the entropy information is transmitted when the noise is amplified by instabilities in the potential. And information is not transmitted when the noise is blocked by the stability of the potential. So from this point of view, you can interpret the score function and the potential energy as a sort of filter. Okay? Essentially, the noise is the thing that transmits information, right? And what the score does is that it blocks the transmission in direction where it doesn't want things to be transmitted. Okay? So in a general, because otherwise you will get white noise, right? Obviously, the maximal bandwidth is when the score is equal to 0 everywhere. So these things are a bit paradoxical. In the sense that the score is a negative rho. The score function is a negative rho. In the sense that when the score function is the largest, essentially there is nothing to the side. And a reason is that the score, again, is an average, right? Between, let's say, if you have data points around you, so the score will be an average with respect to different data points. Okay? And if you have an average, up to normalization term, but imagine that these vectors are normalized because usually the norm doesn't play a big role. If you have an average, the average will be always smaller than the individual vectors because of interference, cancellation. Okay, so there is destructive cancellation. So essentially, the points in which the entropy production is higher are the points in which the score is the smallest. The entropy production is maximized when the system is maximally undersized, because when the system is maximally undersized, the system can transmit all the noise. When the system is very decided, essentially the noise is completely blocked, so the noise is not all. So yeah,
I'm just trying to picture it. It's like, say I'm walking through some landscape. In moments where I'm not sure where I should go, I'm probably walking more slowly.
Yeah.
But I already see the goal, I'm going to walk very fast there. Is that the intuition I should have for this?
Yes. So it's not just the speed, but that is true. So if you see the fastest, you are at the fastest if you can see directly the goal.
Yeah.
In fact, if you can see directly the goal, effectively you can go in one single step. And but it's not just the speed; it's also that in some sense, yeah. If you don't know where to go, you probably will go slowly. But in this case, you will also wander around. You know, it's not that you're just going slowly. You are also sensitive to. But it's not about not knowing, because if you think about not knowing where to go, there is one place where you want to go, right?
Right.
In this case, is that you could imagine that you're going deciding. In Paris, you could visit the Eiffel Tower or the Arc de Triomphe. And then you start walking around, and at some point you see the tower.
Sure.
Okay, and then you start going towards the tower, right?
Is it like critical slowing down?
So you need to always be very careful. So because these are dynamic phenomena, so I think it's connected to critical slowing down, but there is this layer of interface you need to make to the fact that you are mapping to a non-equilibrium thermodynamic system. Okay? So it is connected, but you need to actually, if you want to make it very formal, you actually need to do some groundwork for so yeah.
Also something you can use maybe also like for the inference problem, like we're saying, if you know where you're going, then you can just go there in one step, right? Like now, it feels like if you have like a large space in your kind of your inference diffusion process where you're not adding information, like maybe that's something that you can optimize for. Like you only want the parts where you're adding. That makes sense.
Yeah, exactly. So our solution, and it works very well now for language applications that we're doing, and also for image store, is that essentially you want to use this information rate as time. So the problem in diffusion, that in diffusion, time is arbitrary. You can always apply a monotonic transformation to the diffusion process, and that would be a valid diffusion process. That is not a data-dependent choice. It's completely arbitrary. And if you take infinitely many function evaluation, it doesn't really matter, right? You're just rewarping the time axis. You're just changing your clocks. The problem is that if you usually would take equal space steps, and if you take equal space steps, then it does matter because you essentially, if your time is miscalibrated, you are essentially not spending any time in the part that are important, right? Yeah. So what you can do is that you can redefine time as the entropy itself. Once you redefine time as entropy, so you write down your forward process in terms of entropy, then the equal space will do exactly what you're saying. So if there is no entropy, so if the entropy is zero, it would just jump there. So you will not get any grid content. Okay? So we call that like entropic time warping or entropic time change. And effectively, so the nice thing is that I'm not showing the formula here because I want to keep this talk a bit more conceptual, but you can rewrite this in terms of just the square loss. So effectively, the conditional entropy rate, I'll give you the formula on the board. The conditional entropy rate, H, like 0 given xt, this is simply equal to, so this is SNR, the derivative of the SNR divided by SNR squared. This is just property of the forward process times epsilon square of t. And epsilon is the square error, the denominator. So epsilon is just the average error, prediction error of the denominator. Well, okay. This is just the prediction of the model. So the nice thing is that this is actually your training loss. So effectively, you don't need to compute anything. It's quite beautiful because you are already computing this quantity, but as soon as they give you mathematically the conditional entropy rate that then you can use both for calibrating the noise level during training, because that's also important, right? You need to calibrate the noise level, what noise you're sampling during training, and for spacing your function evaluation. And this is very important when you work with data that are different than images, because in images things are very well calibrated. So if you just use a package it will usually work well, But if you're trying to, I don't know, to just do language, right? That you have a series of symbols, and the diffusion process needs to go to one of the symbols, then the entropy profile looks like this, okay? Because most of the decision making is made at the symmetry breaking points, But if you have images, the entropy profile looks like this. Images have details at all scales. So since the images have details at all scales, the entropy peaks at zero. Okay? It's not necessarily the most useful entropy because it's often Gaussian entropy. Essentially, when the model itself can be quite simple next to zero. Okay? Because most of the images there, it just need to have a bit of detail. So there is not necessarily a huge amount of learning to be done because it can be done efficiently with few parameters, but it has a lot of information because the information content of images peaks at low frequency. Okay. Therefore, if you use a diffusion sampler calibrated for images for here, you will end up essentially what the model is doing here for language is just a rounding operation. Okay, so you will get a very expensive model evaluated hundreds of times for replacing a round that you could have done with no expense in your computer. Okay, so that becomes very important. That is my work. It's a bit biased. So said, if you work with discrete data with diffusion, use entropy, at least for sampling, because that's it's most likely near optimal. Not a mathematician, we didn't spend too much proving it, but it's an enormous improvement. It would be for training. For training is mostly for training. The improvement is less enormous. For training, what you get is that this becomes very reliable. So if you use the entropy as the scheduler for training, usually will work well and will be close to the best you can do. Yeah.
So even for images, this statement that you have this well-calibrated profile because you have details at every scale, it seems very dependent on the type of image you want to generate.
But they're almost always, from the point of view of the spectrum, it's just rare to have substantially different spectral profiles.
But if this optimized entropy-based profile is for free, basically, why is not everybody just always doing this on the fly?
Because a lot of models are converged to trial and error. So most images are so essentially people have been working a lot just by this is just a single function, right? Okay. So the functions that people arrive at by trial and error are quite good. Are quite close to the best you can do. Okay. So you can beat them, they're not unbeatable, but you will not get a huge market.
Sure.
But for stuff like language, it's that people have not been working with this kind of things for a long time, so there has not been as much research for optimizing it. But for stuff like language, people are effectively doing it. It's just that it's coming up now, you know. But remember, like even if you're in a very big lab, if you say like a PhD student, okay, optimize the diffusion model for chemistry, what I will ask you to do is to take a model developed for images and use it for image. And usually it would work. It would work fine. You're just far away from the optimum, you know. So I think that in the future people will move towards. It's just you're not forced to use entropy. There are other possible ways to do it. But whenever you work with discrete data, or it's quite different data, you end up using a solution for solving the problem. And in my opinion, the entropy is the most principle and extremely easily available.
So ChatGPT 5.5 thing doesn't use the entropy one now. They just use the standard profile.
Wait, ChatGPT is another principle. You mean the diffusion?
The diffusion part.
For images, you don't need.
They just use the standard.
For images, you don't need. They're extremely well calibrated. Yeah. So that's the essential. The noise scheduling is extremely well calibrated for images. So by practice, you're right on. So here I showed you what it was TDIM, right? You will not see this. If you take modern models, you will not see this because they're already initializing here. Is it because they understand symmetry breaking? No, it's because they found by trial and error what is the best point to initialize the schedule, you know. So the fact that it's not an enormous amount of information, it's one function of time at the end of the day. So you can get, and does not have a crazy shape. So you can get very close to the optimal you can do, but an error, right? Images for diffusion is being 99% of the effort that you spend. So for images, you just use what is there and just close to the optimum. Is it exactly the optimum? No, but
percent saving in cost for OpenAI would be hundreds of millions.
I mean, I don't know what they're doing. It's just that for them, it's much cheaper to just do exhaustive evaluation than you say. Just like the way that a lot of companies are doing research and development, often it's just they have a lot of computing, so they just say, okay, let's try all possible options, and we pick the best. So that's and often it works, right? So that's we rarely just go for specifically theoretically motivated things because they don't necessarily need to. Okay, so here is something that I've done quite recently that is still a bit of work in progress. And the idea is that this kind of symmetry breaking event I discussed before, they are kind of, from the point of view of machine learning, they're kind of memorization transition. Okay? Because the score, this is the exact score, and the exact score already remembers essentially the landing point, you know, in this case, plus and minus one. This does not happen only in memorization, right? For example, in language, let's say you have binary language, right? Then this decision will happen, even if the score is not memorizing. But in general, often they come up with when the score knows exactly there is an image here and an image here. So these are, formally, this is a bifurcation that is finite dimensional, that does not scale with the image size, you know? In the sense that there are only two options in this case, and even if the image is larger, there will still be two options for having this kind of shape. Okay? From the language of the statistical physics, this is not an extensive quantity. Okay? So the property do not change as you naively increase the dimensionality. So what I'm interested is, if you think about generating images, so you need to really specify not just like the class of the image or a discrete set of parameters, right? But sometimes you need to really to specify the structure of the image, the structure of the pattern, right? If you think about a pattern like this, there is an infinite possibilities that you have. Even if these patterns are binary, the number of decisions will scale with the size of the pattern. Okay? And now, can we still find this kind of symmetry breaking bifurcation or phase transition in the situation in which essentially we expect the number of decisions to scale with the size of the image? Okay? And at the limit, it becomes kind of theoretical or infinite dimension. Okay? And then instead of looking at loss of stability around few eigenvectors, we will actually look at global loss of stability across a continuous family of eigenvectors. Okay? And what you can show. So before, this is a bit a recap of what I showed you before. That effectively, what I've been doing for the symmetry breaking is study the Jacobian around the point, the symmetric point can be around zero, and you can show that if you are finite a number of patterns, the Jacobian will always look like this. Okay, like for the process that this is variance preserved. So look at this. This looks a bit like a Hopfield matrix. So it's quite interesting. If you look at the stability structure at zero, it is kind of makes sense, right? Because you are linearizing, but it is a kind of a structure of a Hopfield network. It doesn't have the same dynamics, so, but it kind of encode this kind of this second order statistics. Makes sense, right? You're looking at the second derivative. Now, if you find a number of data points, remember that each of these mu would be a single data point. If the number is small compared to dimensionality, each data point will be roughly an eigenvector, okay? And will correspond to its own loss of stability. So for a small number of data points, essentially you can track individual decision events corresponding to loss of stability corresponding to individual patterns, okay? The cleanest way of seeing is that if you have a pattern has its own mirror and its own mirror, like if you have mu and minus mu, because then you will actually have an exact symmetry. Otherwise, the loss of stability will be a pattern versus everything else. It's a bit annoying mathematically because it shapes the point of equilibrium. But essentially, if you have a few number of data points, you get into memorization regime, and then you can see the memories encoded in the instability structure of the Jacobian. Okay, with individual destabilization of the eigenvalues, so eigenvalues vanishing. So loss of stability is always an eigenvalue vanishing, and then that eigenvector becomes unstable. Okay, because then it will flip some, so that the noise is amplified along that eigenvector, leading to a final decision. So it's nice that you can reduce that in normal form, like as a bifurcation system, and then you can just study the bifurcation behavior around that specific around the specific direction. And this is a single direction destabilized. But if you want to start studying generalization, you will get in a situation though in which the network does not have the capacity to remember individual data points. And this is quite natural. If you think about the thermodynamic limit, very large images, if the network is finite, at some point it can just not remember not even a single image, because it does not have enough parameter to fully encode images. What the network needs to do is to translate the global patterns that come from the system. It's global, right? If you look at these things, these are global because these mu vectors are large vectors that represent a full image. Okay, so these are global patterns. But if you get in a memorization scenario, these global patterns cannot be directly encoded. So what the network will instead is to translate this global information into local structures or into structures. Okay? And you can generate images that are locally consistent And what I mean to this, which the model cannot remember individual parts. A few years ago, obtained by taking an expectation over a finite data set. Separately at any given point, but only over the space of possible patches. So I don't look at global data points, global images, but I chunk the images in patches, and then I compute the score locally in the patch space. Okay? So this gives me an analytic model, this analytic tractable model of a score that can only encode local information. Okay? Because its maximum radius of dependencies depends on the patch size. It is not a very good diffusion model, so we can generate quite interesting thing, and it's defined by the space of patches. So, for example, if you choose like white and black patches, you get this kind of ferromagnetic behavior in which nearby pixels want to stay of the same color, either white or black. Now you can study, since this is all analytical, you can actually study the properties of this patch score model. And from my point of view, I care about studying the linearization around the point of equilibrium, because it will give us an example of a truly kind of infinite dimensional or extensive bifurcation that happens. And so the nice thing is that this being a patch score, it means that the Jacobi matrix, so a patch score is by definition translational invariant. And there is a standard result that a translation in the invariant model will always have a Jacobi matrix in convolution form. Okay, so it will be a so-called Topliss matrix or convolution matrix. Means that I can diagonalize it. So if you have a convolution matrix, this can always be diagonalized in cross form, and you can get an expression for taken values. Okay? And so what you can show is that if you take the limit of larger and larger images, first of all, taken vectors will become Fourier components. Actually, I think that is always the case, like even in this specific case. But taken vectors in this case are Fourier components. Okay? So instead of using this patch score, instead of having the individual patterns as eigenvector, now eigenvectors become a Fourier basis. Okay? So what it will define the structure of stability is in Fourier basis. And the Fourier basis comes from translational invariance. So it's not just true for the simple model. Any convolutional network for large and large images will actually be diagonalized by Fourier basis. Okay?
Independent of which patches you use.
Yeah, that's completely independent. It just comes from translational invariance. So regardless to what it could lead you to anisotropy. So if you use anisotropic patches, it becomes more complicated. But the Fourier representation is just if you have translational invariance, you will get the Fourier representation. So now we know that for translation equivariant networks, the structure of stability is described by what's happened to Fourier components. And what you can also show is that that you can express the eigenvalues in this kind of informal, just simply by doing a Taylor expansion. And this is a form that would be very familiar to a physicist, because essentially it's the kind of Ginsburg-Landau dispersion relationship. Okay? So the whole structure of instability here is described by essentially the dynamics, with respect of these eigenvalues, because these eigenvalues determine the dynamics of the system, right? The linearized dynamics of the system. And you can interpret all these terms. So what you will see is that the first term that is going to destabilize, what Fourier frequency from this formula, what Fourier frequency is going to destabilize first? Destabilize means that this is equal to 0 for a given time. If you say this equal to 0, I want. Which one?
Low frequency.
the frequency is going to destabilize first because this term is positive, right? And this term k is generically positive. So what will happen is that yes, the low frequency will destabilize first, and then so the important thing that then when you look at the infinitely large images, you will get that the zero frequency destabilizes first, and then there is a continuum of frequency that destabilizes right afterwards, but without spectral gaps, okay, without spectral separation. So you get the full spectrum, essentially, if you have the spectrum like this. If you have the spectrum, imagine that there is this bar of stability and the bar goes down. The first, and this is like zero, right? So the first point that stabilizes is the zero frequency, okay? And then as the bar goes down, there is a continuity of frequency that is stabilizing, okay? And this is the infinite dimensional path, okay? So the instability start with the zero mode, but you have an infinity, a continuous infinity of modes that destabilizes right afterwards. And that's essentially what seeds the pattern formation in this translation invariant mode. Because effectively the patterns comes from Fourier modes that are excited when the system is unstable. And actually, if you see here with this kind of patches, you will see that most of the generation is in between these two. So again, most of the system, you see that between these two and between these two, almost nothing is happening, very fine data. So all the pattern is kind of generated here. Because there is this kind of cascade of instability that happens essentially all of a sudden, and then things freeze again, right? Because then stability, think about the potential reclosers, and then the system is essentially locked in place. Okay? So the difference here, compared with what I said before, is that you get in the thermodynamic limit of large images, you get a continuity of decisions made, which means that the system does not decide just between two classes or two patterns with a point. It relies between an infinite possibility of fields. Okay? So that is why I like to go to pattern formation.
But the fact that it first chooses the lowest mode, does that mean that it sort of decides, well, I mean, mostly white or mostly black?
In the beginning, it's the very thing. It's not that there's continuity, so it's not that there is never one, there is not spectral separation.
Yeah.
So it's never really stuck there. It's as soon as you start deciding about that, you start deciding about the low frequencies in general.
It's like is a zebra white with black stripes or black with white stripes? Like it kind of doesn't matter, but you.
Yeah. So don't think that there are sequential decisions before. That is the expected value. Yeah. So mostly white, but as soon as an infinitesimal amount of time, there will be an infinity of other frequencies that are stabilizing. So you don't think about the individual zero modes. Just think. So those are what they are called soft modes. Can show you like that experimentally. You can see this very clearly. Like this is in a patch score model. So this is nice and analytical, and you see that these are the derivative of the. So those are the taken values. So these are taken values for different Fourier components, and the color that give you the frequency. You see, and around this point, you see that there is a big dip of all the low frequencies, while the high frequency essentially stay in place. So there is a cutoff, so not all frequencies are going to stabilize, right? Because that formula there is only true up to the nonlinearity. So at some point, the linearity kick off, high frequencies can be completely untouched. Okay. But you see, there is this gradient. You see, the lowest frequency destabilize the most, and then you have the nice things. You actually see this in train network as well. So this is a train network, completely random architecture on fashion and NIST for also small images. So quite. But you can see that the dash is the zero frequency, but then you can also see lower frequency destabilizing. So it's actually quite simple. If you have a convolutional model. Even if it has some attention component, as far as mostly convolutional, you will see this soft mode structure. And this is a kind of memorization, okay? And here you don't see any. So if there are only two patterns, as far as those two patterns are not Fourier frequencies, usually you will barely see anything because the instability is not very aligned to the Fourier basis. Yeah.
So what's convolutional about this model trained on MNIST?
Oh, this is just a convolutional. Sorry. This is a component, and this is the patch score. Okay. I have also results here for this is a component. This is an EDM2 model. So this is a quite decently large model on ImageNet. An EDM2 model is convolution, but it's also a decently strong attention component. But I was quite surprised there is a quite strong soft mode effect. You see. Now, so this is not a straight line. The reason is that this is a variance exploding model. So in a variance exploding model, the eigenvalues soften progressively because the Gaussian become. So in a variance preserving model, the Gaussian goes to a fixed point. So the eigenvalue converges to a fixed point. In a variance exploding model, the Gaussian diffuses more and more. Okay, so the average eigenvalue tend to soften. But you see that there is, on this trend, there is this large softening of the soft mode and on several low frequencies. And I'm not showing all of them, right? So I'm showing a sample of around frequencies. Yeah, so actually, if you even go to recently large training models, like the convolutional on pixel space, you will see this soft mode instability quite clearly. And this corresponds to the onset of kind of pattern formation. Because if you look at the covariant structure of the image itself, you will see that the point of instability is the point in which the correlation structure of the image starts ramping up. See, before it's flat, it's a bit easier to see the invariance exploding. This is the correlation structure, the level of correlation between pixels before it's flat. Then there is this point of instability, and then it kind of ramp up, and then it just stabilizes. So we kind of see that. Remember, it's an instability, so nothing really special happened at that point from your point of view, you know? Because it's like if you start falling, nothing special happened when you start falling, you know? It's just that things accumulate from that point on. It's kind of a seed of instability. The noise but the interesting part that most of the decisions are made there for these simple things. But most of the structure of the pattern is made in this very narrow band because for all the other places, essentially the potential is very sharp. So the model will make deterministic decision, but a deterministic decision is not a decision.
So by definition, you wouldn't be able to tell by eye. Because as soon as you're able to tell by eye, it means you've already kind of.
Okay, nothing happens. Yeah. So that is the frustrating part compared to equilibrium statistical physics, because that in equilibrium statistical physics, you work with thermalized systems, you know, and then they have special properties. In this case, the out of equilibrium phase transition, essentially nothing happened at the point of the phase transition, you know, just things start rolling down. So the phenomenology becomes a bit more difficult to extract than in equilibrium physics. Because it's not that the correlation length, in equilibrium physics, you would say that the correlation length diverges. But that needs, if you freeze the potential there and you leave the system thermalized, you will see the correlation length diverge, you know? But an equilibrium system does not freeze, you know? So in equilibrium statistical physics, the shape of the potential is fixed. And then you let the noise go to infinity. You need to the system integrate for infinity with a Lagrangian system. And the system will equally distribute. And if there is instability, the correlation length will go to infinity. The reason is that perturbation will spread, but they need an infinite amount of time to spread. You know, that's why equilibrium is a concept that is quite, it requires the system to be fully thermalized. So in this case, you cannot study the correlation length directly because the noise does not have time to propagate correlation. And the problem is that the noise will not just propagate the correlation in an equilibrium way, because after you are outside of the critical part, then nonlinearity start to kick off, you know. So again, the phenomenology is a bit stuck with this.
Yeah. But do you look at the entropy production here?
I have not done it yet.
Because in some paper, very toy system, they look at non-equilibrium system, which is the double well potential. And so double well is basically the setup you have there, and they see the entropy production peak at the critical point.
I'm sure that it does. I have no doubt that it does peak. I mean, so it peaks slightly after, right? The reason is that the entropy production was the negative part in this of conditional entropy, because in stochastic thermodynamics there is a slightly different definition. So in this adapter I described, it peaks slightly afterwards because essentially it peaks where there is instability, you know. Mm-hmm. So, but instability is not just about the existence of negative eigenvalue, because they always exist, right? But the problem is that if you're here, yes, this area is highly unstable, but there are no particles here, so it doesn't matter, you know. So in the point right after the symmetry breaking, there are particles in a very unstable area. That's the peak of the entropy production, because the noise is highly amplified. Because it's on average, so the entropy. So that is the difference. When you look at the symmetry breaking, you're just looking at this point, you know, and you don't care whether this point is typical or not. So yes, you can still look at this point here, but it does nothing because particles are not there. When you look at entropy production, you average over what is likely, right? But you average according to the probabilities. Mm-hmm. And here you have this magic time in which the probability are still high in the unstable part, you know. As a small aside, just I've never thought about how much consequence you can get from the fact that by definition unstable times are very brief, you know. In like in the theory of evolution, people puzzled by the fact that most of the time species are constant, and then there are very sudden evolutionary changes. But it becomes kind of obvious if you think about it. When something are unstable, they move fast, you know, by definition of being unstable. And when you are in a stable point, you're going to be in a stable point for most of your life, by definition of being stable. I think this thing connects quite nicely with population biology. So actually, for interdisciplinary stuff, I think it's a thing that I would like to look at some point. Um, so that's kind of it. Thank you very much.
Question for Luca? Yeah.
So just my understanding, this last most option paper, the theoretical analysis you do in the black and white patch,
Yeah.
where you consider specifically the symmetry, like the Jacobian around symmetry solution which is x equals 0. If you wanted to do that same kind of analysis for something more complicated, like n-list or whatever, what would you? Is there something you could consider Jacobian around, or could you?
I will recommend to use the Jacobian at the shells. So in this case, I compute the Jacobian, right? Here I do for something more complicated. I'm not computing this Jacobian perturbation at 0. I'm computing that around the actual images.
Okay.
You see? So it needs to be connected to the actual theory. I didn't work out the full theory. I think that's essentially the equivalent of renormalization. Because effectively it's kind of you need the noise recascade through, and that gives you to the kind of the perturbed state. But you need to derive the phenomenology. Like it's very easy to get the phenomenology at the point of at 0, but the phenomenology at 0 is not accessible experimentally, unless at the very essentially never, because it's in high dimension, you know. So you need to translate the phenomenology to the entropic shell, or you just look at the conditional entropy rate or similar quantities that are by definition at the entropic shell. So that's the kind of the only thing you can do is that for an analytic model you can do, right? If you have a large score model, another thing you can do is that you can do that for the whole data set. If you compute the score of a large data set, you have something over possible images. If the data set is large enough, at high enough noise level, it's essentially indistinguishable to the true distribution.
Yeah.
Because you cannot distinguish individual images. So if you want to look at the first onset of instability, and you take a data set like ImageNet, most likely you can, just by looking at the data itself, you can characterize the spectrum of the instability quite reliably. It's memory intensive because you need to store a lot of images to actually do it. But the fact that you have this thing of diffusion, that when the noise level is high enough, the model essentially always generalizes. Even the memorized code generalizes because images are not distinguishable at that noise level. So you cannot really see that the model is memorized. So if you look at things in entropic shell, the Jacobian is very robustly estimated. So you can, this is I just took an IBM model and I just computed finite differences across with respect to vectors of Fourier components. So it's very simple. You will not see that in stable diffusion because it's later. So if you go to you will imagine, right, that it's later, but it's still multispatial. Try very hard. If you actually try to check in stable diffusion, it breaks the spatial structure in a way that you will not see. Will the system destabilize along other modes? I'm pretty sure that it does, because any multimodal system must destabilize along some modes, but they're not in a stable diffusion, they are not Fourier components. One thing that I would like to do at some point, but if you become very kind of specialistic, is that I would like to do kind of independent component analysis to actually find the direction, because essentially the direction of instability are the first direction of non-Gaussianity, Like you will see direction in which the square component disappear and you only see the quartic component. And that's essentially what an ICA look at. You look at the kurtosis that is sensitive to the quartic component. So you could, if you do an ICA, so if you do if you have noise images and you do an ICA, when start from the noise level and start initially you will not find any independent component. At some point you will find some independent components. Those should be exactly the component that stabilize. Which in this case they are Fourier amounts, so you don't need to. But if like in stable diffusion, you just don't know what they are.
And the reason in stable diffusion they're not Fourier amounts is because it's not convolutional model.
The model is convolutional, but the problem that the latents are not, it has a strong attention components and the latents are not spatially organized.
Right.
So you would expect, because there is still some spatial aspect and there is some convolutional aspect of the model. But I think what's happened is that a lot of high level semantic information is dumped into the lowest frequencies. So I think that there exists. My intuition is that there exists a soft mode, but the problem that is overwritten essentially by the fact that a lot of semantic information is dumped to the lowest frequency. It makes sense because semantic information is everywhere. So if you need to use some Fourier channels to store semantic information, you're going to use low frequency channel. You see? But then it's kind of overriding it's kind of changing the structure because it's a linear structure, so it's sensitive. If you start putting stuff on the top, you will get linear combinations, and those can be very different. So it is interesting. Obviously, if you get that, you could see that also in an architecture that is not convolutional if it works in pixel space and is trained on a lot of data, right? If you have a transformer trained on a very large image data set, it can just pick up the translational invariance of the and then you could, I didn't try, but I wouldn't be surprised. So it's not just the property of the architecture, it's the property of the final result. Effectively.
There is this Luca paper about how even with transformers they pick up spatial flow from the data and this paper that came out.
Sense. I mean, they're learning. Eventually, they're learning what. Even if you just use the exact score of the data at that level, they are converging to the same object at the end of the day. So it is more with convolutional architecture of the fact that by construction for very large images it must happen. This does not mean that it will happen when you check though, because they are trained for a given image size. So a convolutional network can be used for any image size. And if you take any convolutional network and you take the image size artificially larger and larger, it will happen mathematically because that's balance. But it can be that the model is not with translation balance within the size where it's trained. So that sometimes you would say that, sometimes it's not.
Do other invariances lead to other soft modes in some other decomposition that's not Fourier? That you have rotational.
I would say yes.
You get some other decomposition that's not Fourier, but you will also find soft modes there.
I'm pretty sure. I mean, I didn't study that, but you should just get the harmonic configuration effect of the group. So if you have like rotational invariant systems, you should see that like spherical harmonics. So.
Something like that, exactly.
Yeah, that may happen. It's essentially just about representation of the specific group. And of course, also the internal group mapping, right? So now everything that I've done so far, I didn't tell you, but implies this very simple internal group of up and down. If you have like vectors, you can have spherical, you can have all sorts of kind of internal groups that are and that changes the structure of the. It's well known, right? In equilibrium statistical physics, there are what changes the structure of the dimensionality. They are universal transition, right? In the sense that the infrared, they all look the same, and they are labeled by dimensionality and by the nature of the group, like this, of the internal group. Of course, universality for non-equilibrium phenomena is more tricky, right? Because universality relies on perfect thermalization. Universality happens when essentially only the quadratic and quartic component, part of the quartic component survive. And the reason that is the case in statistical physics is that when as correlation spread, the potential becomes scale free. So the potential becomes flat everywhere. So the nonlinear path is pushed at infinity. It's just a theory here, right? If the potential look like this, right? The more you go in the infrared, the more you go far away, and the more you get close to here. So at some point, you just don't see what's happening, whatever complexity there is here is not seen. This happens because you have full thermalization. So the system has all the time in the world fully thermalized. In this case, it's out of equilibrium. So you will not get the pure universality. You will get hint of the universal behavior that you will get if you fully thermalize. Not that in equilibrium, you could fully thermalize if you want. You just freeze the score and you keep running the Lagrangian dynamics. Not sure why you want to do it. It can be a form of error. It can be a form of error correction. Effectively, imagine if you're integrating the diffusion trajectory, you can be accumulating errors. For example, because your score was not very well learned here, or you're using a finite solve. So then, if you freeze the score and you need the system thermalized, it will, as far as the score at this point is correct, it will thermalize to the correct potential. So it will correct the errors that it made before. So there are some actual practical error corrector measures. For example, that actually do this, they do Langevin steps.
If you would do this at this critical noise level, where big precision coming, would you then be able to measure like the diverging correlation limits?
Yes, because you will thermalize with the potential. If the potential is critical, then you will thermalize to a critical degree. But keep in mind that it's not necessarily will give you the correct images though.
No,
so it is a bit subtle. So the problem is that
they will stay noisy.
Okay, so this is the point. If this was a score, I mean, to be honest, this is a point that it's a bit slippery because okay, if it's a score, if it's a true score, then if you thermalize at any point and then you continue, you are completely fine, right? Because it's thermalizing to the correct answer. The problem is for an network like this that has constraints, and it's not really a true score function. You see, because the patch score is not a score. So I do think that if you let it thermalize, you actually alter the distribution that you wouldn't alter if you have an exact score. So said, this should also happen if you have an exact score, you know? So if you have an exact score of an exact data set, if the data set is translational invariance, you should get the same kind of instability. And now this is the paradox that I'm not able to understand conceptually. If you stop at the point of criticality, you can arbitrarily grow the correlation line. Okay? But then it seems that it should change the images.
Yeah.
But it cannot, because if it's a score, because just running a thermalized dynamic does not change the potential, so it cannot change the images.
So with an exact score, is the point that after that critical point, you should be able to run and get the images, or just at any point before or after whenever the score function?
Well,
because you feed the score function at any point in the reverse process and expect and then run the large run sample to affect the.
So if you run the large run sampling, it's not going to change the potential. So it will thermalize to the potential. So you need to run it for infinity. Let's say you run long enough, it will thermalize to the potential. And then you are in the correct potential, so you are free to continue. You know? The problem is that the correlation line would increase, and it's not obvious to me.
Because in real images it doesn't.
Well, it shouldn't, right? Because it doesn't have time to thermalize.
Yeah.
So that's, I don't know. I mean, in real network, you can say that it's not an exact score, but you should see the same instability happening in real images under the true distribution of images, because if the true distribution of images is translational symmetric, it will have the same kind of singularity. And then why you will get the images up? Is it some pathology? Because I mean, the argument works at infinite dimension, right? Like exactly. So maybe when you take the dimension of infinity, one limit break, and maybe that's the reason. I don't know. It's a bit paradoxical.
You had a model with a precise score, right? Where you could.
Yeah, you can use the patch score, but then it's not the true score function.
Right.
So in that case, you don't expect to give you the same result if you thermalize. Because it's not the score function of any data.
And what if you create your data with patches?
That you will get an exact score.
Okay. Yeah. Well, that with a
It's saying that it's empirical. Simple. I'm saying I don't understand it. I think it's interesting. I'm thinking about this. It's just that for me, these are kind of a bit lazy research for the kind of things I do, because usually I do kind of more like applied machine learning, and then I need to stop myself for that. But yeah, I am interested. I'm interested of kind of solving this conceptual paradox, because it's not obvious to me. Because I know that the singularity will happen quite generically. And I know that the amount of thermalization matter. And remember, thermalization is not zero in the diffusion model, right? Because the system will have a finite sweep through the criticality. Okay, so this is what in physics they call the kind of Kimball-Durek phenomenology. It's done in cosmology, and effectively there it's the same thing. Actually, in cosmology, you look a lot like generative diffusion. Not a coincidence. Because effectively in cosmology, the potential is a function of time. The quirk of generative diffusion is the potential, the shape of the potential is linearly coupled to the dynamic time. That's the same in cosmology. In cosmology, the shape of the temperature changes as a function of time. So you get this coupling between temperature and time, it means that the system will only experience the phase transition for a finite amount of time, because afterward it will stop visiting the potential, the critical potential, and therefore you will get a finite harmonization. So instead of the correlation line diverging, you will get the finite peak in correlation. And in cosmology, this tell you about the formation of kind of different topological domains. Like, actually, I don't think that this is known. So in the current standard model, this disappointment does not happen. The reason is that the electroweak phase transition, I don't know. The electroweak phase transition is not a true phase transition in the sense that it's not a true symmetry breaking. It doesn't correspond to different laws of physics. It breaks the gauge of the theory, but it's just a level of description. It breaks your description of the theory, not the theory itself. So, because symmetry breaking was discovered in the context of this electroweak phase transition, it's just that the different Higgs states do not correspond to different physics. They just correspond to different descriptions of the physics. So said, in larger gauge groups that we could be in or not, there are topological sectors. So there are things that are not true locally, but the model can need to make topological decisions. So you will have some patches of the universe that can have a different physics than other patches of the universe. And the rate of formation of these patches comes from this cable zoom. Because the system will go to the phase transition for only a finite amount of time, and then will correspond to the formation of the bubbles. And inside of this bubble, there will be different laws of physics. I think that, yeah, something like the theta sector in QED could play like that, but that's not broken. So the symmetry case is not broken. So, and not a part of this, but it's a cool. Yeah, but the model that using phenomenology, essentially you could use it if you want here as well. My main point is that so it's a bit difficult to extract the phenomenology because I must have a training in equilibrium statistical physics, and the phenomenology is much more difficult to extract, because you're not letting the system formalize. So defining the observable is difficult because the observable at the criticality are essentially not observed, except for the Jacobian itself, except for the potential itself, that is very reliably extracted. So that the soft modes in the Jacobian as well, you can see, but all the interesting kind of propagation of perturbation, you need to kind of track things dynamically, and it becomes quite tricky and quite sensitive to the way you do.
Well, that's it. So thank you, Luca.